Benzene derivatives generally produce signals in 5 characteristic regions of the IR spectrum. These 5 regions and the vibrations associated with them are listed in the table here and can be seen in the IR spectrum of ethylbenzene, which is shown right here. Notice that the signal is just above 3,000 reciprocal centimeters, so meaning these ones right here, corresponding with sp2 hybridized carbon-hydrogen stretching, appear on the shoulder of signals for all other carbon-hydrogen stretching just below 3,000 reciprocal centimeters, and these ones just below come from sp3 hybridized carbon-hydrogen stretching. This is often the case, and these signals can be identified by drawing a line at 3,000 reciprocal centimeters. So something we like to do is take our ruler out, and we'll draw a line right at 3,000. Is that vertical? Close enough. We'll draw a line just like that, and that makes it easier to recognize those sp2 hybridized carbon-hydrogen stretches. Aromatic compounds also produce a series of signals between 1450 and 1600 reciprocal centimeters, resulting from the stretching of carbon-carbon bonds of the aromatic ring, as well as ring vibrations. The specific pattern of these signals can often be interpreted to identify the specific substitution on the ring, meaning whether it's mono, substituted, ortho, or meta or para, whatever, although this level of analysis will not be discussed in our current treatment of IR spectroscopy. Back in the chapter on nuclear magnetic resonance spectroscopy, we discussed the anisotropic effects of an aromatic ring. Specifically, the motion of the pi electrons in the ring generates a local magnetic field that effectively de-shields the protons connected directly to the ring, meaning they're going to have a higher chemical shift than you might expect. The signals of these protons typically appear between 6.5 and 8 parts per million. Now take a look at the NMR spectrum of ethylbenzene that's shown here. The presence of the multiplet near 7 parts per million is one of the best ways to verify the presence of an aromatic ring. Notice that the de-shielding effects of the aromatic ring are felt most strongly by the protons connected directly to the ring. Protons in the benzylic positions are farther removed from the ring and are de-shielded to a lesser extent. These protons generally produce signals between 2 and 3 parts per million. Protons that are even farther removed from the aromatic ring exhibit almost no de-shielding effects. And so you see that the quartet for this methylene here, which is in a benzylic position, you see they're pretty de-shielded, and the reason why is because they're attached directly to the aromatic ring, which causes that de-shielding based off of anisotropy. The integration value of the multiplet near 7 parts per million can be useful information because it indicates the extent of substitution on the aromatic ring, meaning whether it's mono, di, or tri-substituted. An integration of 5 in the aromatic region is indicative of a mono-substituted ring, whereas if you have an integration of 4, that would mean that you have a di-substituted ring, and so on. The splitting pattern of this multiplet is generally too complex to analyze because of the rigid planar structure of benzene causes long-range coupling between all of the different aromatic protons, even some of the non-aromatic neighbors. Therefore, the substitution pattern is usually pretty complex, except in the following 2 para-substituted cases, both of which produce very distinctive and simple patterns. So if we have a para-substituted aromatic ring and our 2 substituents are identical, in this case, all 4 of the aromatic protons are going to have the exact same chemical shift, and they're all chemically equivalent, so they don't split each other. And so we're just going to see a singlet that integrates for 4 protons. On the other hand, if we have para-substitution and we have 2 different groups, X and Y, in that case, we're going to get 2 signals. Why? Because these 2 protons are going to be chemically equivalent, so they don't split each other. They're too far away anyway. And these 2 protons are going to be chemically equivalent. And so what are we going to see? We're going to see 2 doublets, right? This proton is split by 1 proton, so it gives you a doublet. And this proton is split by this guy, and so we see a doublet. So we see 2 doublets that integrate for 2 protons. So when we see this, it means we have a para-substitution, but we have 2 different substituents. Also, oftentimes, these 2 doublets can be leaning in towards each other. Forgive my bad artistry, but sometimes they can be leaning in towards each other like that. Now back in the NMR chapter, we also looked at carbon-13 NMR spectroscopy, and the carbon atoms of aromatic rings typically produce signals in the range of 100 to 150 parts per million in a carbon-13. The number of signals is very helpful in determining the specific substitution pattern for substituted aromatic rings. Several common substitution patterns are shown right here. If we have something that's para-substituted and both substituents are identical, well, in that case, we only have two signals because we only have two unique types of carbons. Whereas if we have a di-substituted compound that's ortho and both substituents are identical, in that case, we have three signals because we have three different types of carbons. Four signals, there's a few different scenarios we could have there. We could have meta-substitution when both substituents are identical, or we could have para-substitution when both substituents are different, or we could have monosubstitution. That would give us four signals in the aromatic region as well. Now, six signals, when we have all six carbons being different, that would be when we have two different substituents but no symmetry. So the two possibilities would be if we have X and Y that are ortho to each other, or X and Y that are meta to each other.